Hi, future doctors. I am Dr. Salam Hamdi, anesthesiologist intensivist at Sahlul Academic Hospital, associate professor in anesthesiology and intensive care, affiliated to the Faculty of Medicine of SUS. In today's educational medical short video, I will talk to you about gas exchange versus oxygen transport. Gas exchange is reflected by PaO2, while oxygen transport is reflected by SpO2. Consider that you are as a student in ICU and you see the pulse oximeter of one patient showing SpO2 of 92% and the arterial blood gas reports PaO2 of 65 millimeter of mercury. It's legitimate to ask these questions. Are these numbers saying the same thing? Is one more important than the other? The answer is no. They measure two different steps in the journey of oxygen from the lungs to the tissues. Understanding this difference is essential for interpreting oxygenation correctly. As I mentioned earlier, oxygen travels from the lungs to the tissues, and in this journey the first step is the gas exchange in the lungs, where PaO2 represents the amount of oxygen dissolved in plasma and reflects how efficiently oxygen moves from the alveoli into the blood. In other words, PaO2 tells us about lung gas exchange. If the lungs are impaired, for example in pneumonia, adult respiratory distress syndrome, or pulmonary edema, oxygen transfer becomes less efficient and PaO2 falls. So PaO2 answers an important question. How well are the lungs loading oxygen into the blood? The next step in oxygen journey is the oxygen transport step, where SpO2 represents the percentage of hemoglobin molecules carrying oxygen. This reflects the blood's capacity to transport oxygen to tissues. And to understand why this matters, consider the equation for arterial oxygen content, given by the equation as you see, 1.34, which is the capacity binding of hemoglobin, multiply hemoglobin, multiply SpO2. The second part of the equation is 0.003 multiply PaO2. And if you look carefully at this equation, the first term represents almost all the oxygen carried in the blood. And it depends, as you can see, on SpO2, not PaO2. The second term represents the oxygen dissolved in plasma, and its contribution is extremely small because of the factor of 0.003. Let us return to our patient with his SpO2 of 92% and PaO2 of 65 millimeter of mercury. The saturation is still acceptable, but the PaO2 tells us something important. The patient is approaching the steep portion of the oxyhemoglobin dissociation curve. At this point, even a small drop in PaO2 can produce a rapid fall in SpO2. So PaO2 acts as an early warning signal about lung gas exchange before saturation falls. In practice, saturation is an excellent continuous monitor of oxygen transport, while oxygen partial pressure of arterial blood helps us assess lung gas exchange. These two numbers are useful, but they answer different physiological questions. In conclusion, PaO2 reflects gas exchange in the lungs. SpO2 reflects oxygen transport by hemoglobin. Remember the oxygen content equation and remark that the coefficient 0.003 shows how little dissolved oxygen contributes to total oxygen transport. So when interpreting oxygenation, always think of the whole chain and journey of oxygen from the lungs to tissue via blood transported by red cells. Second, understand the physiology behind the numbers, and the numbers will make sense. Thank you, and meet you in other educational medical short videos.